Now, the factors that determine the acidity, there are different factors that determine the acidity of an acid. Instead of using the pKa table, you can refer to these factors in there, because the pKa table is not always available. And it's not always convenient to use it. So this is why if you go with a set of rules, you can easily determine which acid is stronger. The idea is when your conjugate base is stable, your acid is strong. So you have to figure out, you have to change always the acid into a conjugate base and figure out, is that conjugate base stable? If it is stable, then the acid is strong. So always draw the conjugate bases, figure out if it's stable, and then if it's stable, then your acid is going to be a strong acid. Let's have an example over there. So let's have an example there. So what do we have here? Okay, we have water. I am asking which one is this be a stronger acid? Is it water or CH4? Now it's easy to figure it out from the pKa table. pKa table of alkanes is always more. So the pKa value of alkane is always more than water. The pKa for water is always 15. So because it's a neutral, it's always 15. So water is going to be a stronger acid than methane, than CH4. But let's go ahead and apply the conjugate base rule and the stability of the conjugate base. So we're going to change the acid. So this is the acid. So assuming that this is my acid, okay, and this is an acid over there, although this is not an acidic hydrogen. But if this is an acid and this is an acid, which one is the strongest acid? Change this acid into its conjugate base, take a hydrogen out. Change this acid into a conjugate base, take this hydrogen out, and see which one is more stable. The more stable the conjugate base, the stronger is the acid. Now, stability has to do with the charge on the electronegative atom. So if you have a negative charge, the negative charge normally prefers to be on an electronegative atom rather than on on carbon. If you take a look at the trend of the electronegativity in the periodic table, you have carbon, you have nitrogen, and you have oxygen in period number 2. Electronegativity increases from left to right in a period. So this means that oxygen is more electronegative, carbon is less electronegative. Normally the negative charge prefers to be on the more electronegative carbon than the less electronegative carbon. That will make the structure stable. So OH is more stable, OH negative is more stable than a C negative. Because think about it, a negative charge is an indication that you already have electrons. And since carbon is less electronegative, carbon does not bear a negative charge. We don't prefer to have a negative charge on the carbon. We always prefer, if you want to put a negative charge, put it on the most electronegative element, like halogens and like oxygens in there. They bear more than negative charge. They are more stable in there. So in order to determine the acidity, the first thing we're going to go over is elements in a period, in a row. So elements in a period. There is a difference between a hydrogen connected to a carbon, a nitrogen, oxygen, fluorine, and hydrogen connected to a group, elements in a group, like hydrogen connected to fluorine, chlorine, bromine, and iodine. There's a big difference in those. So whenever a hydrogen is connected to elements that belong to the same period, like carbon, nitrogen, oxygen, and the fluorine in there, the acidity increases of the hydrogen as the electronegativity of the anion or as the electronegativity basically of the acid of the A increases. So as the electronegativity increases of these atoms, each of these atoms in there, as the acidity of the hydrogen increases. So this is why you see fluorine is more electronegative than oxygen, than nitrogen, than carbon, Because fluorine is more electronegative, then the hydrogen that is connected to it is going to be more acidic. Why? The rule is the following. Because basically the fluorine is more electronegative. It's going to pull electrons towards itself. It's going to steal electrons from the hydrogen and make it more partial positive. The more partial positive the hydrogen is, the more acidic it is. So this hydrogen is more acidic than this hydrogen, then this hydrogen, then this hydrogen. What do I mean by this? I mean by this, it's more acidic. This means that if I have a weak base, the weak base is going to take this more acidic hydrogen. But if I have a weak base here, this is a weak acid and weak base, the reaction won't proceed to completion. Okay. So let's go back over here a little bit. So if you can take a look here and see, okay, if I change each one of those into its conjugate base, so I have an F negative there, I have an OH negative here, I have an NH2 negative, and then I have a C negative. Why I'm doing this? Remember when I said that in order to figure out the acidic hydrogen, always change the acid into a conjugate base and double check and see if your conjugate base is stable or not. A conjugate base is stable if the negative charge is on the more electronegative element. So the conjugate base of HF is very stable because F has a negative charge. The conjugate base here has a negative charge on the electronegative element. Oxygen is more electronegative, or fluorine is more electronegative than oxygen. So fluorine bears the negative charge more than the oxygen in there. And then carbon there is going to be the least electronegative. So this is going to be the least stable conjugate base. This is the least stable conjugate base. So its acid is not going to be strong. This is going to be the most stable conjugate base, so its acid is going to be very strong. Now this is in case whenever you have acids that belong to a period. In this slide, if you have acids that belong to groups, this means that I am comparing now between a hydrogen that is connected to a fluorine, chlorine, bromine, and iodine. Okay? These halogens, they belong to a group, they don't belong to a period. For elements that belong to the group, you have to look at the size of the anion and not the electronegativity. The bigger the size of the anion, so let's go ahead and change over here these anions. So you have your HF, this is my acid. The conjugate base here is F minus. Here the conjugate base is the Cl minus, here the conjugate base is the Br minus, and here the conjugate base is the I minus. Of course, you need to write all the lone pairs in there. Okay. Now, what do I mean by that? Look at the size of these anions there. From 115, the size, basically the atomic size, increases as you go down the column. So as you go down the column, the atomic size increases. So iodine has a bigger size than bromine, than chlorine, than fluorine. Fluorine is a smaller anion, so its conjugate base is a smaller anion. Iodine is a bigger anion. Conjugate base is very big. Now, take a look at this negative charge. See all of these electrons, they present an electronic cloud around the I minus over there. The negative charge is spread over a larger surface area. And this is why the size of the anion really matters in its stability. The bigger the anion, or the larger the size of the anion, the more basically space the electrons are spread So this charge is spread or delocalized over a larger surface area in there, which stabilizes the anion. So that I minus now is going to be very stable because the negative charge is spread over a larger surface area. Then the Br, then the Cl negative, then the F negative over there. To make this, then this means that this is a more stable conjugate base because the charge is spread over a larger surface area. This is the same idea for resonance. So this charge is spread over a larger surface area is going to be a more stable conjugate base, then its acid is going to be the strongest. So if I am comparing between each of these acids, HI is going to be the stronger acid and HF is going to be the weakest acid. You don't go by electronegativity, because if you go by electronegativity, it's going to give you a wrong answer because fluorine is more electronegative than iodine. So always go with elements in a group, always go with the size of the element in there, or of the anion, and the larger the anion, the more area the charge is spread over. This is going to make that anion more stable, and if that anion is more stable, then its acid is going to be stronger. So this basically summarizes what I'm talking about. Without referring to the pKa table now, which compound is a stronger acid. So all what you need to do over here is just figure out. So let's go ahead. You can work with any single hydrogen here because all of those hydrogens, they belong to an sp hybridized carbon. So here you have a carbon connected to a hydrogen, and then here for water you have basically a hydrogen connected to the oxygen in there. So I'm looking for an HO and I'm looking for the CH over here. I know that oxygen is more electronegative than carbon. Then basically water is going to be more acidic. So water is going to be more acidic in this case. You can also change the water into its conjugate base, which is the OH minus, and change the whole thing into its conjugate base, which is basically this. And you can easily see that the negative charge on a less electronegative element is less stable, then its acid is weaker compared to a negative charge on a more electronegative element, then its acid is stronger. Now with respect to a CH and an SH, because this is going to be this is a sulfur over here. So you have your sulfur there and then the hydrogen. Okay, so let's see. You have a CH, you have an SH. Let's change both into their conjugate bases. So this is the conjugate base over here. You have a C with a negative charge. This is my conjugate base, which is the S with a negative charge in there. Which one basically is more electronegative? Sulfur is more electronegative. So in this case, this is going to be a more stable conjugate base. It's the H2S is going to be more acidic. Over here, I do have NH. These are not hydrogens. These are carbons. So these are carbons. So in C, I'm just going to go ahead and write it over here. In C, this is an N, CH3, CH3. I'm just writing over here. It's a skeletal, and this one is in the condensed form over there. So which one is the strongest acid? When I'm talking about the acid, I don't look at the lone pairs in here. I mean one of these hydrogens in there. So I'm going to put this as a 2. Okay, I'm just going to go ahead and put this as a 2. And now we're talking about this hydrogen over here, this hydrogen. So comparing, is this a stronger hydrogen or this hydrogen over here? Which one is a stronger hydrogen? Just see how it is connected or where it is connected to. This hydrogen is connected to a nitrogen. This hydrogen is connected to a carbon. Nitrogen is more electronegative. So definitely this is going to be a stronger acid. Or you can change this into its conjugate base. change this into its conjugate base, whatever you want, okay? And then C, the negative charge has to be on the more electronegative element to be stable. So the conjugate base here is more stable. It makes the acid stronger. So this is why this is stronger there. Same idea over here. Which one is a stronger acid? So stronger acid, I no longer look at the lone pairs here. I'm gonna look at the hydrogen over here on this carbon. So you have 3 hydrogens over there. Here you go. These are my 3 hydrogens over there. This is a carbon connected to a hydrogen and oxygen connected to a hydrogen. So this is gonna be more acidic because the oxygen is more electronegative than the carbon. Or you can do as we did over here, change this into a conjugate base. This is my conjugate base. Change this into a conjugate base. This is my conjugate base. And the conjugate base here is more stable because the negative charge is on the electronegative element. It makes its acid more acidic. Between H2O and H2S, so let's go ahead and draw the Lewis structure in here to see where the hydrogen is connected to. Here you go. Go ahead and do the conjugate base for each one. So you have the HO negative, you have the HS negative. Now notice here I no longer have the right to go with the period. I need to go with the group because oxygen, sulfur, they belong to the group over here. And as the size of the ion increases, it is basically more stable. And the size of the atomic size increases as you go down the group, or the as you go down the group in there. So sulfur is a bigger size than oxygen. Because sulfur is a bigger size than oxygen, then the negative charge is spread over a larger surface area. So sulfur here is a bigger anion. So the negative charge is spread over a larger surface area, which makes that conjugate base more stable than the C over here. So the H2S is going to be more acidic. Water and H2F, then our HF. So this is going to be my water, this is going to be my HF. Change this into a conjugate base, F minus. Change this into a conjugate base, HO negative. See, the negative charge is on the more between oxygen and the fluorine. Oxygen and fluorine belong to the same period. So I have to apply the rule of electronegativity. If I am working with elements in the same group, I have to apply the rule of atomic size. So oxygen and fluorine's rule of electronegativity. Fluorine is more electronegative. It bears more the negative charge. So it becomes more stable anion. Its acid is stronger acid. So HF is going to be the stronger acid. Stronger acid. Okay. Which hydrogen is the most acidic? So you have hydrogen A. This is a carbon connected to A. This is a carbon connected to a hydrogen, nitrogen connected to a hydrogen, oxygen connected to a hydrogen, sulfur connected to a hydrogen. Of course, between these 3 over here, between A, B, and C, this hydrogen is the most acidic. But when you compare hydrogen C with hydrogen D, of course, hydrogen D is more acidic because sulfur is bigger in size than oxygen. So it's basically a more stable anion conjugate base than oxygen. So which hydrogen is more acidic? It's definitely hydrogen D is more acidic. Now the second rule for seeing which acid is stronger is the inductive effect. What is this? Inductive effect is caused by electronegative elements, and it's the pull of the electronegative elements, is the pull of electrons due to the electronegative element through the sigma bonds. Let me give an example over here. This is an example. So if you have an acidic hydrogen, and if this acidic hydrogen is close to electronegative elements, so what these electronegative elements would do, these electronegative, now I know that oxygen is an electronegative element and it's very close to the hydrogen. So oxygen is going to pull electrons away from the hydrogen there, leaving the hydrogen partial positive. Same thing here. It's going to pull electrons away from the hydrogen and it's going to leave the hydrogen partial positive. However, in this compound in here, you do have further additional electronegative elements, and these electronegative elements are going to pull electrons. See, they're going to pull electrons away from the hydrogen through the sigma bonds towards the fluorine. So now what you can see over here is that the electronic cloud is distributed. It is not focused on one region. The electronic cloud now is distributed through over the whole structure. Here, the red region is normally the region that represents the electron rich, where electrons are. And here in this case, in the ethanol, this is the ethanol, the red region is basically on the oxygen. It's here. It's basically on the oxygen. This is my oxygen over there. This is my O, and this is my hydrogen. The red region is on the oxygen, so telling me that this is my electronegative element. The electronegative element is stealing electrons from the carbons, from the hydrogens, and now my electrons, they reside in one place on the oxygen. While here, the electrons basically, they are distributed. See, the red region is basically throughout the whole structure in there. It's not confined in one region. It's a spread, and this is the idea for stability. It makes the conjugate base more stable. If your charge or if your electron density is spread over a larger surface area, it's going to make your conjugate base more stable. So the conjugate base over here is going to be more stable because your electrons basically, they are distributed over a larger surface area rather than having the electrons just focused on the oxygen. So in this case, if you compare between alcohol, between ethanol and this compound, the first thing I would do, I would consider the conjugate base for each. I would lose the hydrogen for each and get their conjugate bases, and then see which of these conjugate bases are stable. The stability has to do with the distribution of the charge and the electron density. And remember, we always want the charge and the electrons to occupy a larger surface area for the conjugate base to be more stable. And this here forms a more stable conjugate base than the ethoxide in this case. Now, with respect to the fluorines, fluorines are electronegative elements. These electronegative elements they withdraw electron density. This is the chemical term that we use to explain basically the role of the electronegative fluorine and what they do to the lone pairs on the oxygen and basically the electrons on the hydrogen. They withdraw electrons through the sigma bond. So when they do this, they distribute the electron density more across the structure. They stabilize the conjugate base. If they stabilize the conjugate base, then the base is stable. Then its acid, it's going to be a stronger acid in that case. So which compound in each pair is a stronger acid? Both are carboxylic acids. See, this is my acidic hydrogen here. This is my acidic hydrogen over there. So I already answered this partially. So this is an acidic hydrogen, this is an acidic hydrogen there. But which one of these acidic hydrogens is a stronger acid? Well, you need to look and see what type of electronegative element it is connected to. I know that fluorine is more electronegative than chlorine, then bromine, and then iodine. So fluorine is going to withdraw electron more in that case. And if I look at the conjugate base for, okay, so if I look at the conjugate base for this guy over here, this is my conjugate base now for it. This is my fluorine. And I'm gonna have my conjugate base here. This is my conjugate base. See, the fluorine is more electronegative. It's gonna pull electrons away. It's gonna pull electrons away through the sigma bonds, and it's gonna distribute the charge all over more than chlorine. Chlorine is less electronegative. Chlorine still going to pull electrons, but not as strong as the fluorine. So this is the negative, this is my chlorine over there. Chlorine still is going to pull electrons away from this oxygen in there, and it's going to spread the charge or the electron density over a larger surface area. So this is stable and this is stable, but the pull of electrons is more for the fluorine because fluorine is more electronegative. This is going to make that conjugate base more stable. It's going to make that acid stronger acid. The stronger the chlorines are or the electronegative are elements are to the hydrogen, to the acidic hydrogen, the more acidic the hydrogen is. Reason why? Because do the conjugate base for it. See, do the conjugate base over here. You have a chlorine, you have a chlorine. Chlorines are closer to the electronegative element in there. So basically, they're going to pull the electrons away. They're going to pull the electrons away and distribute the electron density throughout the whole structure. This is one carbon separation between the chlorines and the oxygen that is connected to the hydrogen. This is two carbon separation. So now the chlorines are farther away from the hydrogen. If they are farther away from the hydrogen, their inductive effect, which is the pull of electrons through the sigma bond, is lower. So their withdrawing effect is going to be lower. They won't reach the electrons of this hydrogen. So this one is going to be more partial positive than this hydrogen in here. So it's going to be this hydrogen basically in structure, and this structure is going to be more acidic. Comparing between these two over here, this is an acid, this is an acid, so I'm looking at these acidic hydrogens. Now notice what do I have in here? NO2. What is NO2? NO2 is called an electron withdrawing group. It's similar to chlorine, similar to fluorine. Now, chlorines, fluorines, iodines, bromines, these are electronegative elements. So you already know that they pull electrons, they steal electrons away. What about this nitrogen? How do I know that it steals electron and it's called an electron withdrawing group? This is when drawing resonance is handy, okay, or drawing a Lewis structure is important. Please draw the Lewis structure. NO2 is this. To know if a group is withdrawing or not, it should have a plus charge. It should have a positive. It should have a positive charge directly connected. So here the nitrogen has a positive charge. It can either have a positive charge or partial positive charge, one of those. So the nitrogen is having here a positive charge. So if it has a positive charge, this means, just to check this, I'm having nitrogen. This nitrogen is more electronegative than carbon. So this is a carbon, this is a nitrogen. So the nitrogen is going to pull electrons from the carbon. See, this is the inductive effect. It's pulling electrons from the carbon in there. And then I'm having oxygens there. The oxygens are more electronegative than the nitrogen. Then also they're going to pull electrons. So see now my electron density here. My electron density, this is the conjugate base. My electron density is basically distributed over a larger surface area. It's no longer contained on the oxygen. So the oxygen here is not a red region. The red region is distributed over the whole surface area in here, which makes the conjugate base here more stable. So if the conjugate base is more stable, the acid is going to be stronger. So acidity has to be determined by electronegative elements that normally withdraw electrons. We call them electron withdrawing groups. Electronegative elements can come in form of halogens. They can come also in form of groups. So if you have NO2 in there, this is basically a withdrawing group. The reason why? Because the nitrogen has a positive charge. So if nitrogen has a positive charge, it is a withdrawing group. One more thing I want to say over here. If I have this structure with a double bond O and an OH, and I have an OH here. See, the OH, the difference between an OH and an NO2. The oxygen in here has lone pairs. It doesn't have a positive charge. So the oxygen here gives electrons by resonance. It donates electrons. It does not withdraw electrons. When you donate electrons, you decrease the acidity of the hydrogen because the hydrogen will no longer be partial positive. When you withdraw electrons, that hydrogen will be more partial positive, then it will be more acidic. So donating groups closer to the hydrogen, acidic hydrogen, will decrease the acidity of the hydrogen. Withdrawing groups closer to the acidic hydrogen will increase the acidity of the hydrogen. Then the third effect is the resonance effect. The same idea. You need your conjugate base to be stable. If your conjugate base is stable, this means that the charge or the electron density is spread over a larger surface area. So it's exactly the same thing. Here I'm comparing between ethanol and acetic acid, and we're seeing which one is a stronger acid. So you change each one of those into their conjugate base, changing ethanol into its conjugate base, changing acetic acid into its conjugate base. The rule is conjugate base is stable when its electron density is spread over a larger surface area. So the electron density should just be spread over a larger surface area. So in resonance, the electron density normally is represented by the negative charges. So over here, ethanol doesn't have resonance there. Or when it has resonance, you can do resonance in here, and then you're going to end up having a plus a charge on the carbon and a double bond over here on the oxygen. So this is the only resonance in there for the ethanol. So the negative charge basically is focused on the oxygen for the conjugate base. See, the oxygen has the region which is filled with electrons. Now, with respect to the acetic acid, if you do resonance in there, so resonance delocalizes the electrons. It basically spreads the charge over a larger surface area, and it makes the conjugate base more stable. So now your charge is no longer focused on just one oxygen. No, it's distributed between two oxygens. So this is the same idea. When you distribute your electron density or you distribute your charge over a larger surface area, then your conjugate base is going to be more stable, then its acid is going to be stronger. So which one is a stronger acid? We're going to go ahead and do conjugate bases for each one of them. We're going to do resonance for it. We're going to see which one has resonance in there. Now, this guy over here doesn't have resonance. It's an oxygen that has a negative charge. This guy over here has basically three resonance structures, 1, 2, and 3. And the negative charge basically is distributed between the two oxygens. It's very important when your negative charge is between two electronegative elements. Here, the negative charge is between a carbon and an electronegative element. See, I can do another resonance structure in there, make the negative charge on the oxygen. So your negative charge is on the oxygen here, your negative charge is on the less electronegative element, which is a carbon there. So if I am comparing which one is the most stable conjugate base, it's this. Because this stable conjugate base has the negative charge on two electronegative elements. So this is why acetic acid is going to be the strongest acid. See, its pKa is the lowest. So this is going to be the strongest acid. Okay. Now, with respect to these two over here, the difference is this oxygen is on a negative charge. This negative charge is on an oxygen, and here, although I have a resonance structure there, and the charge is distributed, but one of the resonance structures has carbon to be negative. This is not stable. This guy over here is not stable. So this is why if you take a look at the pKa's of methanol and acetone, you're going to see that this conjugate base is more stable than any of these two conjugate bases, because this conjugate base bears the negative charge on the electronegative element. This conjugate base has the negative charge on a less electronegative element, which is a carbon. So this is why methanol is going to be a stronger acid than acetone, and the strongest is the acetic acid. Which anion is a stronger base? Again, look for the stability. So if you look at the stability in here, resonance always stabilizes the anion. Um, it's normally if resonance stabilizes the anion, then it's gonna be a stronger acid. If it's a stronger acid, then it is a weaker base. I'm asked here which anion is a stronger base. Well, this one over here is the conjugate base of this acid, and since it's very stable because of resonance, so this is the acid in there, because of resonance this acid is going to be a strong acid, then its base it's going to be a weak base. It's resonance stabilized anion. Why? Because I can draw resonance structure in here. This is my resonance structure, showing both resonance structures in there, and how the basically the negative charge is distributed between two oxygens in there. So I have an oxygen over here. So how the negative charge is distributed between the two oxygens there. This is going to be a stable conjugate base. Its acid is strong. This means that its base is going to be weak. Over here, the negative charge is only on the oxygen. There is no possibility for any resonance. So if the conjugate base is not stable, then it's not very stable. So its acid is weak. If the acid is weak, then the base is strong. So always you refer it to the acid. See the strength of the acid. What is it? If the acid is strong, the base is weak. If the acid is weak, then the base is strong. And then the last thing is hybridization. This is basically the last section of how to figure out which one is a stronger acid, which one is a weaker acid. So hybridization, when your hydrogen is connected to an sp3 hybridized carbon, compared to an sp2 hybridized carbon, compared to an sp hybridized carbon. Electronegativity, in terms of electronegativity, an sp hybridization is more electronegative than sp2 than sp3. The reason why? Because electrons are pulled more towards the nucleus in the sp compared to the sp2 compared to the sp3. So if electrons are pulled more towards the nucleus, this makes, see those lone pairs, they are closer to the nucleus. If they are closer to the nucleus in this case, that is going to make the anion more stable, because the lone pairs are closer to the nucleus rather than far away, from being far away from the nucleus. So this is it. This is what I have over here. When they are closer to the nucleus, this is how they look like. And as you can see, the red region basically is distributed there. They are closer to the nucleus, rather than the lone pairs in there. They are far away from the nucleus, and here they are farthest. They are just confined in this region over here. So the closer the lone pairs are to the nucleus, the more stable is the anion. The more stable the conjugate base, the stronger is the acid. So always hydrogens that are connected to an sp hybridized carbon, they are stronger acids, or hydrogens that are connected to an sp hybridized carbon, they are stronger acids than those connected to sp2 than those connected to sp3. So let's have an example here. Okay, so let's have an example. Which hydrogen is more acidic? I already drew the product for, or the answer for this one, instead of wasting time writing it. So which acid is more acidic in each pair? Again, this is an sp hybridized carbon. The electrons are pulled more towards the nucleus. Why? Because it does have more S character. The S character is 50% out of the total number of orbitals. You have here two orbitals, 50% S, 50% B. And I know that lone pairs basically they are in the they are basically, or electrons, they are in the s orbital, and the s orbital is the closest to the nucleus. So so this guy over here, this is its conjugate base. Conjugate base is stable, so it is more acidic. This is an sp3 hybridized carbon. This is its conjugate base. The conjugate base is going to be this is going to be a less stable conjugate base. in that case. So this is going to be a less stable conjugate base, so its acid is going to be less acidic. It is pretty much a stronger base. So this is a stronger base than this structure over here. So this is why I said this is a stronger base. Stronger base, weak acid. Strong acid, weaker base, weaker conjugate base. Between these two, between an sp2 hybridized hydrogen or sp2 hybridized carbon connected to a hydrogen and an sp3 hybridized carbon connected to a hydrogen, of course the sp2 is going to be more acidic because its conjugate base is more stable in that case. Draw the conjugate acid of the following bases. So I have these three bases. I want to draw their conjugate acids. Just add hydrogens to them. So I added hydrogens to each one of them, and then rank the bases in terms of increasing basicity and their conjugate acids in terms of increasing acidity. Just remember that in terms of acidity, you need to go with electronegativity. So Sp is more electronegative than Sp2 than Sp3. So a hydrogen that is connected to an sp hybridized carbon is going to be more acidic than that connected to an sp2 than that connected to an sp3. Let me go ahead and put the hydrogens over there. So these are the hydrogens that I'm targeting over here. This is the sp3 hybridized carbon. This is the sp2 hybridized carbon over there, and this is the sp hybridized carbon over here. So these are the three hydrogens that I am comparing with respect to the acidity. Of course, the stronger the acid, the weaker the conjugate base. So the stronger the acid, the weaker the conjugate bases. So the weaker the bases. So these are the rules that we've covered so far. So as a summary, in order to determine which acid is the strongest, always change into a conjugate base and figure out which conjugate base is more stable. Stability can go according to electronegativity. If you are working with a period, elements in a period, it can go according to size if you're working with elements in the group. If you're working with resonance, then look at the charge distribution and see if you have resonance in there. If you have resonance, then your charge is distributed over a larger surface area. It makes the anion more stable. And if the anion is more stable, then the acid is more acidic. And then check for hybridization. Hybridization, you look for Sp is more acidic than Sp2 than Sp3. And of course, don't forget the withdrawing groups. The closer the withdrawing groups are to the acidic hydrogen, basically the more partial positive the hydrogen is and the more acidic is the hydrogen.